Welcome to our second optimization session. This one is on how to optimize query performance in Azure SQL. We will start off by first defining and then analyzing query plans and some best practices on how to identify problem areas. We will then show best practices for both evaluating query improvements and reviewing table and index design. Lastly, we will give best practices to ensure that the changes we have made to the query or to the design have had a positive effect on performance. Let's take a look at how to explore query performance optimization here in SQL. The most important skill you should acquire in database performance tuning is being able to read and understand query execution plans. The plans explain the behavior of the database engine as it executes queries and retrieves the results. Query Store helps you to quickly identify your most expensive queries and find any changes in performance. By automating the collection of query plans along with the query execution runtime, the Query Store provides a powerful, complete data collection. SQL Server and Azure SQL provide locking and blocking in order to manage concurrency and ensure data consistency. In this section, we will talk about how to save them, how to compare them, and how to understand what they are trying to tell us about our query performance and more in this section. Execution plans are critical components of SQL Server performance generated by the Query Optimizer to determine the most efficient way to execute a query. When a query is run, the optimizer evaluates multiple potential plans and selects the one with the lowest estimated cost based on statistics it gathers about the data and operations involved. These plans are stored in plan cache as XML for reusing, also helping us to reduce overhead on future executions, and it's critical for performance tuning, as they determine how resources like CPU and memory are used during query execution. Accurate statistics are essential as they influence memory grants and operator choices. Poor estimates can lead to excessive memory allocation, resource semaphore waits, or TempDB spills. Benefits include dramatically improved query performance, often 100 to 200% gains without hardware upgrades, and it reduces the manual tuning that we're going to have to do. Benefits include faster query response times and reduced resource consumption, while use cases span from optimizing complex joins and filters to troubleshooting slow-running queries in high-volume transactional systems. The Query Optimizer takes a query and returns a query plan. Here we see how SQL Server generates and executes query execution plans to optimize query performance. When a query is executed, it first goes through the parsing and binding, producing a logical tree of operations like table reads or joins. In parsing, it is looking to see if the syntax is correct and if the objects that we are requesting exist. If either is incorrect or missing, it throws an error. But if both are correct, it moves on to the next step. The Query Optimizer then generates multiple physical execution plans and assesses their resource and time costs. It selects the plan that is not always the one for the best and fastest performance, but usually the one that is good enough for its best guess for performance to use. And it passes this to the execution engine, which may cache the plan for reuse in plan cache. This process ensures efficient query execution by leveraging statistics and system settings. Getting a plan is CPU intensive. Benefits include faster query performance, reduced resource consumption, and minimized manual tuning. Use cases range from optimizing complex queries in large databases to troubleshooting slow-running queries caused by stale statistics, missing indexes, or poor design. Cached plans and accurate statistics can lead to performance improvements of up to 200%, far exceeding gains from hardware upgrades alone. Listed here are 3 essential types of execution plans in SQL Server: the estimated execution plan, the actual execution plan, and the live query statistics, each serving a unique role in query performance analysis and optimization. The estimated execution plans are generated by the Query Optimizer to compile time using existing statistics to predict the most efficient path for data retrieval, including memory grants and operator choices. The actual execution plan extends this by capturing real execution metrics such as actual versus estimated row counts, CPU time, and execution warnings, helping identify discrepancies and performance issues. Live query statistics combines both views into an animated, real-time visualization of query execution, showing row flow and operator handoffs, which is especially useful for troubleshooting long-running or complex queries. These tools benefit database administrators and developers by enabling proactive performance tuning, reducing resource bottlenecks, and improving query efficiency in both development and production environments. Use cases include diagnosing slow queries, validating index effectiveness, and refining execution strategies without altering application code. Here's a note on some of the differences between actual versus the estimated execution plans here in SQL Server. Estimated execution plans are generated without running the query and provide a preview of the operations the optimizer intends to perform, making them useful for quick assessments with no performance impact. In contrast, the actual execution plan includes the runtime statistics, such as account row counts, actual row counts, and memory usage, and offering deeper insights for troubleshooting by requiring the query to be executed, which can be very time-consuming or even impractical for certain operations like one-time updates. Despite their differences, both plan types share the same structure and operator order and are essential tools for database administrators to identify inefficiencies, optimize queries, and improve resource utilization. Lightweight query profiling highlights a performance-friendly method for monitoring query execution in Azure SQL databases and in SQL Server. Unlike traditional profiling methods that introduce up to 75% server overhead, lightweight profiling, especially when enabled at the query level in a newer SQL Server version, offers a much lower impact, typically around 2%, making it ideal for production environments. It requires the trace flag 7412 to be enabled globally for systems prior to 2019. It helps bridge the gap between estimated and actual execution plans by providing real-time statistics without the heavy cost of capturing full actual plans. This is particularly useful in scenarios where capturing actual execution plans via SSMS or extended events would otherwise degrade performance, such as during live site troubleshooting. Benefits include real-time visibility into query behavior, improved diagnostics, and safer performance tuning. Use cases include identifying regressions, validating optimizer choices, and supporting proactive monitoring with minimal disruption to running workloads. How to interpret SQL Server execution plans effectively is a learned skill, starting with guidance to read plans from right to left, top to bottom, which mirrors the actual data flow in the execution plans, as we will see shortly, and helps us to understand the sequence of operations. The size of the arrow between the operators visually represents the volume of data being passed, helping to identify potential performance bottlenecks due to large data transfers. Each operator contains rich metadata accessible via tooltips, offering insights into how the optimizer made its decisions. This is crucial for diagnosing inefficiencies. Operators are also assigned a relative cost, allowing users to focus tuning efforts on the most resource-intensive parts of the plan. Importantly, even operators marked with 0 cost still consume resources. It just means that it's below 1%. These helps are really beneficial for performance tuning, query optimization, and troubleshooting in both development and production environments, especially when analyzing complex queries or addressing slow-running workloads. Here is an example of a typical T-SQL join query and its corresponding execution plan, offering a detailed view of how SQL Server processes a query. The query retrieves product names, calculates the cost per outer box by multiplying unit price and quantity per outer, and returns the quantity on hand. It performs a join between the warehouse stock items and warehouse stock items holdings tables, and it does a match between stock item IDs, and then it sorts the results by the computed cost per outer box. As we view the execution plan here, it visualizes the sequence of operations SQL Server uses to fulfill that query. On the bottom right, Clustered Index Scan reads all the rows from the clustered index, indicating a full table scan. This can be bad for performance depending on how big the table is that needs to be scanned. Generally, when you see a clustered index scan, that usually means that SQL cannot find any good index to use to retrieve the data, or the amount queried for is so big that it's easier for it to just scan the table rather than pick the results from the table. We then see a compute scalar operator that calculates the cost per outer box expression, and then a merge join operator that efficiently joins the two tables using sorted inputs. Notice that the clustered index scan on the stock item holdings ID field is likely missing a non-clustered index, as it has performed a scan here. But the merge join is one of the best joins for performance. The sort operator orders the results by computed column, which can be a costly process here, with 37% of the total processing time spent here. Consider having the end user app do the needed sort. Lastly, the select operator does the final output operation. Note that each operator is assigned a relative cost percentage, helping identify performance bottlenecks. Here are a few considerations. Indexes that you create and use today are for the data that you currently have in your tables. As time goes on, the data can get bigger and, of course, change. Once unique values in fields that use the index you've created may become not as unique in the future and not use the indexes that you've created. Also, queries that your users use can change over time too, requiring that you reassess your indexes. You need to assess indexes and their use periodically, and remove the indexes that are not being used and make new ones to be used. Remember that indexes take up space, they need to be maintained, and they're critical for fast running of your queries. Using composite non-clustered indexes usually give you the best performance. It's also better to have one index on a table that includes the fields that your users commonly query for, and ordered by quality operators first, columns that have the equal or the in, and then inequality columns second. Those are columns that have like with the not equal to symbol, or the greater than symbol, or the not in. And those would be added in the include statement. So a little bit of guidance there for us. The tooltip highlights the cost and estimates for the estimated plan and the actual plan. This will include comparisons to the actual rows and the cost, and it can be obtained by hovering over the execution plan operator. The properties include some additional information, and it shows the output list, which provides details of the columns being passed to the next operator. These columns, in conjunction with the clustered index scan operator, can indicate that additional non-clustered indexes might be needed to improve performance of the query. It can be obtained by right-clicking the query plan operator and selecting properties. The execution plan will also highlight any missing indexes along with the T-SQL to use to create the missing index or indexes. It can be extremely helpful. There are many plan operators in the execution plan. Here are a few that find data during your query. We have the index seek operator, which is efficiently used here to retrieve rows from a non-clustered index by using the seek predicate to target only relevant data, while the index scan operator reads all rows from the non-clustered index and applies an optional where clause predicate to filter results. Both are logical and physical operators. The table scan operator similarly retrieves all rows from a table, applying a where predicate if present to limit the output. And the key lookup operator performs a bookmark lookup using a clustered index and is always paired with a nested loop operator, which relies on the clustering key specified in the argument column. Lastly, the table valued function operator executes a table valued function and stores its output in tempdb, returning rows to parent iterators upon request. Your goal is to get your query to run as fast as possible without increasing resource costs. You can override the operators that Query Optimizer chooses, and if you do that, it will extract your data using query hints. But it is not recommended unless you're testing your indexes, usually is when we use that. The key lookup in any kind of scan are potentially bad for performance and may require a deeper dive into why it's being used, which we're going to explore coming up. Check out the cost of each operation and try to reduce the cost of the operators that are consuming too much processing time and resources. More to come on this topic coming up. Here are more plan operators in the execution plan, this time for filtering and sorting queries. The nested loops operator executes various join operations, inner, left outer, left semi, and left anti-semi for a few options there, by searching the inner table for each outer table row, typically using an index. The hash match operator builds a hash table from its build input into the hash predicate, and then it probes it for matches looking for the same matching hash function. Both of these operators and merge joins are used in joins. The best performing one is the merge join. Next, nested loop, and lastly, hash match join. The hash match join and the sort can both be really costly. The top operator returns a specific number of percentage of rows from the input, potentially based on sort order. The sort operator organizes incoming rows and may include distinct order by or order by predicates in its argument column. Lastly, the stream aggregate operator groups rows by one or more columns and computes aggregate expressions, which can be used by subsequent operators or returned to the client. Dynamic Management Views, or DMVs, and Dynamic Management Functions, or DMFs, in SQL Server are powerful tools that provide real-time insights into server and database health, performance, and diagnostics. These objects categorized as either server scoped, requiring view server state permission, or database scoped, requiring view database state permission, enable administrators and developers to monitor system behavior, troubleshoot issues, and fine-tune performance. All DMVs and functions reside in the sys schema and the following naming convention, DM_*, and must be referenced using a 2-part, 3-part, or 4-part name in T-SQL. DMFs allow up to 3-part names. Benefits include proactive performance tuning, faster issue resolution, and enhanced visibility into the resource usage. Use cases range from identifying slow queries and tracking memory usage to auditing connections and analyzing weight statistics, making DMVs and DMFs essential for maintaining robust and efficient SQL Server environments. The Query Store, introduced in SQL 2016, is available across Azure SQL platforms, including Azure SQL Database, Azure SQL Managed Instance, and Azure SQL Database for MySQL and PostgreSQL. It functions like a flight recorder for databases by persistently capturing and aggregating query execution plans and runtime statistics such as duration, logical I/O, and CPU usage. This enables database administrators to quickly detect performance regressions and pinpoint the most expensive queries, facilitating targeted optimization and troubleshooting. Its integration with the execution plan operators like index seek, index scan, table scan, key lookup, and table valued function enhances its utility by providing visibility into how these operators behave over time, helping users understand when and why certain access paths are chosen. The Query Store's ability to retain historical performance data makes it invaluable for performance tuning, root cause analysis, and ensuring consistent query behavior across deployments. Let's look at some common key use cases for our SQL Server's Query Store. It enables detection of regressed queries. It tracks how often a query runs within a specific time window, and it compares average execution times across intervals to identify performance anomalies. These capabilities help database administrators and developers proactively monitor and troubleshoot query behavior, optimize execution plans, and maintain consistent performance. The Query Store is enabled by default for new Azure SQL database instances. If it's not enabled, you want to use the alter database statement shown here and set the Query Store on with the operation mode set to read-write. This will enable the Query Store to both collect new performance data and allow access to existing data. It will actively record query execution statistics, such as duration, CPU usage, and I/O metrics, and it will store this data for analysis while also making this data available for querying and reporting. Operation mode read-write is essential for monitoring live workloads, detecting performance regressions, and optimizing query plans in real time. The Query Store in SQL Server acts as a data flight recorder for query performance, capturing execution plans and runtime metrics such as duration, logical I/O, CPU usage, and more. These are permanently stored for analysis over time. Its built-in reports in SQL Server Management Studio, like regressed queries, overall resource consumption, top resource consuming queries, queries with forced plans, and queries with high variation, also query weight statistics and track queries, enable database administrators and developers to pinpoint performance regressions, analyze resource-heavy queries, and troubleshoot execution plan variability. These reports can be filtered by time ranges, so things like the last hour, last day, last week. You can also use them for evaluating the impact of server configurations that you've just done, or schema changes, or ensuring consistent query performance across deployments. Collecting data in any system has an execution cost of CPU cycles, memory, and disk utilization, also known as observer overhead. The query store is designed to minimize this impact on its data collection. Data for the query store is written to memory for each new query and for each query execution. If this was written to disk for each execution, the performance overhead would be significant. So SQL Server uses a setting called data flush interval seconds to control the frequency of flushing the query store data to disk. By default, the data is flushed every 15 minutes, but this is a user configurable setting per database that you may want to adjust. You can force plans with the query store, which is a powerful feature in SQL Server that enables database administrators to enforce a specific execution plan for a query, particularly useful when performance regressions occur due to sudden plan changes. Plan forcing offers a quick mitigation strategy by allowing the engine to revert to the last known good plan, and it also drives the automatic tuning feature, which was introduced in SQL Server 2017, and it's also used here in Azure SQL. This automatically applies the last known good plan after detecting regressions. While plan forcing is effective for intermediate performance recovery, long-term stability requires investigating the root cause, such as missing indexes or suboptimal query design, and applying permanent fixes. Together, these features support use cases like maintaining consistent performance, troubleshooting regressions, and optimizing resource usage in production environments. Identifying problematic execution plans is an art as well as a science. It'll take some time to perfect, but here are some of the query execution plan's major performance concerns to watch out for, and more coming soon. First, a warning is flagged by a yellow triangle on the select operation, which may indicate issues like implicit conversions, memory spills to tempdb, or other inefficiencies. Second, the plan reveals a highly expensive key lookup clustered operation, consuming 99.6% of the query's execution costs, which is the cost of retrieving each record from another layer in the balanced tree or B tree structure, likely in this scenario, a heap. While there is no clustered index, to alleviate the key lookup, consider creating a composite non-clustered index for the fields listed in the select clause, fields that you are doing complex math with, the foreign key field, and fields in the where clause. Put them in order of equality columns first. These are fields that use the equal sign or in, and then the inequality columns in the include statement. These are fields that have the not equal or the greater than or the not in option through T-SQL. You may remember that I talked about how it was better to create one index with many fields than many indexes with fewer fields. So we want to kind of consider that here. But here is something better that you could also do. You might want to find out from SQL what are the top 5 or 10, your choice, worst performing queries for that table. Find out what fields all the worst performing queries have in common. And then out of the X number of common fields, let's say there's 5 in common over those 10 tables, you need to figure out which fields have the most unique values. And then you create a composite non-clustered index listing the equality columns first and the inequality columns in the include statement. To optimize the query execution plan, you will usually list a missing index warning with a T-SQL syntax to set up. So that's a good one to look for. Additionally, it's important to assess whether indexes are being used effectively. So scans versus seeks, we want to see more seeks. And then we also will note that sorts may or may not be necessary. So we're trying to minimize sorts on the server end and pass them out to the client, let the client sort as they'd like. And then we're trying to minimize key lookups, which usually can be minimized with a composite non-clustered index. Sargability in SQL Server, which stands for Search Argument Able, and refers to query predicates that are structured in a way that allows SQL Optimizer to leverage indexes for faster query execution. Sargable predicates enable seek operations, and they're usually using non-clustered index on the referenced column. This will significantly improve performance. However, not all predicates qualify. Examples like where last name like %Smith%, and where convert, and we're converting a character for the create date to 121. Things like this, when we're trying to change date, convert dates, or we're using a wildcard to start off with, these are not sargable because they involve functions or patterns that prevent index usage. So the wildcard and the convert functions and others we may want to stay away from if they're not sargable, if our point is to make our query run as fast as possible. While the presence of a sarg increases the likelihood of the index being used, it doesn't guarantee that it will be used. The optimizer may still choose a scan if the index is deemed too costly, especially when the predicate targets a large portion of the table. Important here is if the predicate is not sargable, the optimizer will not even consider a seek operation, making it crucial to structure queries thoughtfully and avoid unnecessary functions on indexed columns. Addressing missing indexes is a critical role of the index management here in SQL Server for improving query performance. SQL Server provides missing index warnings in execution plans, helping you to identify queries that inefficiently scan clustered indexes to retrieve very small amounts of data from very large tables. The most common performance issue faced by database administrators stems from the absence of useful indexes, which forces the engine to read more pages than necessary. Although indexes consume space and can affect write performance, their benefits in speeding up query execution often far outweigh their costs. SQL Server offers dynamic management views, most of which start with sys.dm/db, and one is missing index details, another is index usage stats, and the last one I'd like to mention is our index operational stats. All of these track missing and existing index usage. These tools help determine which indexes are beneficial and which are unused and should be dropped. However, missing index suggestions should be treated as starting points. It's essential to understand key queries and build indexes that support them rather than blindly creating all suggested indexes without evaluating their interactions. Here are some performance bottlenecks in SQL Server that can arise from hardware limitations, particularly under production load. While single query executions may not reveal these issues, they become evident when multiple queries compete for limited CPU threads in memory. CPU contention is typically detected via the performance monitor counter % processor time. And within SQL Server, wait types like SOS scheduler yield and CX packet signal CPU pressure or parallelism inefficiencies. Storage performance issues are flagged by the page IO latch SH waits, and it can be tracked by using disks per second read via disk per second write counters. You'll also notice that SQL Server logs errors when disk I/O exceeds 15 seconds. These hardware factors compound query inefficiencies such as implicit conversions and expensive key lookups, which can consume a lot of execution costs. Using composite, non-clustered indexes, pursuing sargable queries that use index-seek operators, and evaluating your poor-performing indexes can help reduce overhead and avoid costly row-by-row lookups in a clustered index. Hardware performance should be assessed early in troubleshooting using baseline data discussed earlier. Most database performance issues are due to suboptimal query patterns and may be put under undue pressure on hardware. Missing indexes could lead to CPU, storage, or memory pressure. Tune suboptimal queries before addressing the hardware issues, because that's usually the issue. Maintain accurate and update statistics in SQL Server, Azure SQL Database, and Azure SQL Managed Instance to support the cost-based query optimization in generating efficient execution plans. Since the optimizer relies on data distribution insights from column and index statistics, outdated statistics can lead to suboptimal query plans. Although SQL Server automatically updates statistics as data changes, rapidly evolving data sets may require more frequent manual updates to maintain performance. The Query Optimizer engine considers factors like database compatibility level, also row estimates derived from statistics, and available indexes when building a plan. Tools like our sys.dm DB stats properties helps to track when statistics were last updated or how many modifications have occurred since. And the auto update mechanism uses a dynamic threshold that lowers the percentage of the required row changes as the table size increases. Overall, keeping your statistics up to date will help the Query Optimizer make a good execution plan decision. SQL Server uses locking mechanisms to preserve the atomicity, consistency, isolation, and durability properties of the ACID model. Locking is a normal and essential behavior in relational databases, ensuring that concurrent transactions do not violate data integrity. SQL Server employs lock escalation, beginning with fine-grained locks and escalating only when necessary to reduce overhead. However, blocking can degrade performance when transactions are poorly handled, either left open too long due to application logic or slowed by inefficient indexing or external operations like linked server queries. These issues manifest in two ways. A process may hold locks for an extended period, reducing concurrency, or it may fail to release the lock entirely, requiring administrative intervention. Programmers must manage transaction boundaries carefully, while the database engine safeguards table consistency through its locking strategy. SQL Server's isolation levels are essential for balancing concurrency with data integrity. Isolation levels determine how transactions interact with one another, especially in scenarios involving dirty reads, where a transaction reads uncommitted changes, or in phantom reads, where repeated queries return different results due to ongoing modifications. SQL Server offers several isolation levels. Read uncommitted allows maximum concurrency but permits dirty reads. Read committed, which is the default, prevents dirty reads and releases read locks immediately after the operation. Repeatable read retains reads and write locks until the transaction ends, preventing other transactions from modifying the data. And serializable, the strictest level, ensures complete isolation by holding locks until the transaction completes. Additionally, SQL Server supports row versioning-based levels. Read Committed Snapshot is a good option. It's ideal for reporting on OLTP systems without blocking writes, and Snapshot, which provides transactional level consistency but may roll back updates if a conflict arises. These levels can be set at the session level or overridden per query. And while lower levels improve concurrency, they increase the risk of inconsistent reads. Choosing the right isolation level depends on the workload and the need to balance performance and data accuracy. Now let's look at a few strategies for identifying and tracking blocking issues in SQL Server environments. Blocking can be sporadic and difficult to detect, but the dynamic management view sys.dm tran locks, when joined with sys.dm execute requests, helps pinpoint which sessions are holding locks and what statements are involved. When querying dynamic management views, it's useful for real-time diagnostics. A more robust approach would involve using extended events, and that would help us monitor blocking over time, which is available in the Management Studio, the SQL Server Management Studio through T-SQL. This method allows administrators to correlate locks with specific queries and track patterns, making it easier to troubleshoot intermittent issues. What is parameter sniffing? You might be asking right now. It is a key behavior in SQL Server where the query optimizer uses the initial parameter value to generate an execution plan based on available statistics. This default behavior helps reduce recompulations and CPU usage by reusing plans, which can be beneficial for performance. However, if the initial parameter used in executing that query is not representative of typical query patterns, it may result in a suboptimal plan. Local variables, which receive standard assumptions, can sometimes mitigate these issues, but may not lead to less efficient execution. This ties directly into the broader importance of the query execution plan, arguably the most critical aspect of the database performance. While hardware upgrades typically yield modest gains of 10 to 20%, optimizing execution plans through better indexing, updated statistics, and thoughtful design can deliver dramatic improvements of up to 200% or more. Database administrators often face performance problems due to missing indexes, stale statistics, or poor schema design, all of which force the engine to do more work than necessary. Addressing these issues by improving execution plans can make queries run 2 to 3 times faster, significantly enhancing the overall system efficiency. Now it's time for our knowledge check. Question 1. Which type of execution plan is stored in plan cache? Answer: estimated execution plan. Question 2. Which DMV should you use to find index utilization? Answer: sys.dm db index usage stats. Question 3. Which of the following weight types would indicate excessive CPU consumption? Answer: SOS scheduler yield. Now it's time to look at how to identify and resolve blocking issues. Now let's start with lab number 8, identify and resolve blocking issues. This is an excellent lab for working with how to make certain that all of our queries run as fast as possible and how blocks can show up. So what we're going to do is we're going to start it off really inside of the Management Studio. And what I did is I restored AdventureWorks 2017. I'm about ready to refresh it to verify that it's in my list here of databases. And there it is right there. So this is the database we're going to use for this process. And what we're going to do is we're going to go work with the event sessions. Now, there's a lot of ways to handle event sessions, and I think the easiest might be either going through code, which we're going to show here, or through the GUI that I'll spend a little bit of time at the end showing here in a moment. But it's also going to be based on the 2017 database that we're going to use here to have it do some monitoring for us with event sessions. So I'm going to click on the new query here, and then I'm going to go paste in our T-SQL query. This is available in Lab 8, and what we'll see is I'm going to have to create an event session here called blocking, and it's going to be on our server, where it's going to ultimately here be under security. Oh, pardon me, under management, and then into extended events. And we'll see it here under our sessions. Now we're going to see that there's already 3 sessions that are here by default. These come with the installation of SQL, and I could use them if I want to use them, though I have to turn them on. So some of them might not be on, as you can see here, and I can turn them on by right-clicking and choosing that option, but we'll leave them where they're at right now. What we're going to do is create a new blocking event session that will be added to the sessions list. Then I'm going to add an event, which is going to be a blocked process report. And you can see the actions here. I'm going to pick up right here. It gives us a kind of list of actions it will pick up, as you can see. And then we'll see, too, that it's going to have a target. So I'm going to have it write it out to the ring buffer, which makes it easy to view right now. And then I'm assigning it to the maximum amount of memory. And I'm setting the event retention also there to allow single event loss and the maximum dispatch latency, the event size. And so some of these things I can adjust here or later. And then I'm going to start this. So if you just create the event, it doesn't start automatically until you actually start it. So I'm going to execute this, and I'm going to come over here to the sessions, and you should hopefully see that now it's been added to the list. And you can see, too, there's a ring buffer. And what I can do is I can right-click blocking, and I can go into its properties, and I can see specifically what it's designed to do. And it just takes a moment for it to load up here. So we'll let it load for a moment, and then we can see you can watch events live. You can turn this on. Notice it, okay, what it told us at startup. It has a name that's already associated with it. There's templates that you can use. But this event area here breaks down the events that we're monitoring. So it's the block process report that it's working with, and there's additional events, as you can see, that I can pull up and pull into if I'd like and use those. So you have a lot of events to choose from here. You can also click on data storage and say where you want to put it. Right now it's just in the ring buffer, but there's other storage areas that you can pick from this list to see. And then some advanced options were already configured during the code there. But you can see the advanced options, and you may not be able to get to them right here, but we can see that they've been configured already. So what we're going to do is we're going to use this option here. What it's supposed to monitor is blocking for us. We've turned it on, and it will also have a client. It'll pick up the client app name, and it's going to pick up the client host name, and it's going to pick up the database ID, and some of this you can see across the top here. Actually, the database name, the NT username, the session ID. It will also pick up our T-SQL text and then the username. So those are all the things that we asked it to pick up when we created this. And now we're going to do it. Now what we're going to do is we're going to run another query in here. And this is going to do some configuration for us. So what we want it to do with this is we want this command to specify the threshold in seconds where the block process reports are generated. So as a result of this, we're not really going to have to wait that long to see this block process. Sometimes it takes a while for the block process to actually kick in. but we're going to adjust it so that we can see it in 60 seconds or less there. Actually, it's 60 seconds or less. And then what we're going to also do is we're going to go do a transaction and see how that affects our blocking here and make a block here, because it's the begin transaction without the end part, the commit transaction part. So while this transaction is running, it's going to keep running and running until either we roll it back or commit it. So it's going to monopolize that resource. This is updating the person table and changing the last name field there. So we'll execute that. That will be in blocking, because we're going to have to run, this other process here. And it's going to keep open that process and not close the resource or commit that resource for us. And then we're going to try running another query here where we're going to go use the same table. But what we're going to do is we're going to try to have that query run, and we'll see what we get there. So we're looking for the top 1,000 records, including, what we're doing here is we're going to see that if we can get it executed. Now the resource has a block on it because we did the begin transaction without rolling it back or committing it. Best practice is to do your inserts, updates, and deletes inside of a begin transaction and commit transaction. And also you might want to do it between a try and a catch scenario, where it will give you the ability to catch the error if there is one, and roll it back if there's an error, and then release the resource for others to use it. But you can see I'm pretty blocked up here. It's been running 3,839 seconds, and you can see it there in the corner, and it's increasing as I talk. But what you're seeing is that it's going to run for a long time because the resource is blocked. We blocked it from right here. So we will need to note here, and we can see that this block right here. So I'm going to come in here and I'm going to see if I can make some changes to it. And when we do that, I'm going to zoom in a little bit so you can see it here. And we might be able to see it's going to take a couple minutes, but we might be able to see it and pick up some extra information from it. And it's going to take a moment here. And I can click on it and we can see if I can push it out. Okay, here it is, HTML. And we're going to give it a little bit longer to collect that information. And then we're going to go back to it in just a bit. But while this is running and it's executing here, I'm going to open something that we've used in SQL for a very long time, and that's our activity monitor. I'm going to open that up, and this activity monitor is going to show us processes in here. And it may take a moment to show it, but it should be able to see it running. Processes, and then even blocks. So this here, it looks like it's our block. Actually, no, this is one that has been suspended, so it's been blocked out. This one is running, and let me see what it looks like. If I go into this, it's a very tiny window, and I'm going to pull it up here so we can see it, but you can see the little command right there. Okay, so this is another command that is running, and here's another one we can look at right here. We can see the details on this one. And again, it shows up on my other screen, and I'm going to drag it over. It's a very, very tiny window, so I'll make it a little bit bigger. And this one, again, is looking for telemetry. And so we can go look for blocks too and see if we see any, but it takes a little bit for this to kind of pick it up. And we can also see the log, and we can see the database name. You can see some of the fields that it has across the top there, the task state, the current type. We can also see the application name, the wait time, if we have any in there. It has a little bit in there. We can also see the resource weights. This might be helpful. Looks like there's some locking that may not get the detail all the way through just yet. And then there's this statement right here. Let's right-click it and look at the details. And that's what I like about this, is you can go in and you can see what's going on under the covers. And I think this is our block right here. So sometimes it takes a little bit to show up, but there is our block. And it has one little number here. So I think this is showing the block right here. So what I can do is I could kill this process, and I probably don't want to do that unless I'm certain. And then seeing that there's a block, and also seeing that, yeah, there's kind of a longer wait time. So it looks like it could be our block. We could go a little deeper. That might be very helpful to do. The activity monitor gives us the ability to see and investigate running processes, getting into the code, and we can take a closer look at other options in here too. So this block right here, and there's the suspended one, and it looks like it's object 79, which is this statement right here. So you can see the begin transaction statement. So it kind of took a little bit to create, but it created it for us here. And this one here actually has this subnet. So there's two are a little bit related here. There's a 79, and the right of that, you can see the 79 up top, and then it's 82. So 79 and 82 are the two we can see right here inside the activity monitor. And this one's that one that's blocking. So the other one's trying to run and can't run because there is a block. So you can see from the numbers here, we kind of pick them up from the tabs and we match them in. And the activity monitor does give us a lot of information we can dig into. It's kind of a way to go in and discover a bit more. So let's see what we can do now with our ring here and see if it's had enough time to pick up some of this information. And sometimes it takes a while, but it normally will pull in that HTML file so we're able to see it and give us a little bit more information there too. And I'm going to right click it and I'm going to change the interval to 5 seconds. That might help it be a bit more faster as it goes through. We'll also come back and see that I could get impatient right now, and I'm going to click on it and see if I can find it. Okay, here it is. So it takes a little bit to open this up. So I changed the interval on it and it made it run a little faster for us. And I think I like it right here with some of the options here that you can see. So we get the total events processed over 52 in 5 seconds. And then we see how much memory, and I'm just looking at the top here, but we have a block, as you know, so we can go down and it'll give us the database ID, the object ID, the index ID, the lock mode right there. So some of these we might have to get a little bit more information on, but it's a transaction block and it looks like the transaction ID right there and who the owner is, most important there. It tells us it's a blocked process and we know who owns it. So we can glean some of the information here from the HTML if we'd like. And it can go a little further and we can see the block process more detail down below here. And it keeps going. So there's the transaction block. It shows you SPID 79. That's the one we wanted. So that's the one it is here. And then we can also see the other SPIDs here. And we can see them as we pointed out earlier, and it's giving me more information. So in the client name, I have a lot of information there. We just asked it and it's picking this up. Information every 5 seconds, so this is going to run pretty fast here. And it's repeating quite a lot, but I think you get the idea with this. So what I'm going to do is I'm going to go in and let's see. I'm going to go run another command here that will give us maybe a little bit more information. And we could run and actually see a little bit of this. So I'm going to go ahead. I'm going to roll back the transaction for us, but I could let it try this. I might try this, and let's see what we can get. This one, I'm going to have it roll back. Let's try this. So I'm debating on whether to do that, but let's give it a try. I think it's a good option. So let me run the command here, and this is supposed to give us more information first. Even here, you can see the SPID numbers. So this might be a little easier place to look at. It's looking at the event sessions. It's giving us the information on what's blocking. You can also see the begin transaction. You can see a little bit of the transaction from here also, the SPID, and it gives us more information if I scroll to the right here. So you can get a lot of information, the host, the client interface, a lot of different ways as you're seeing. The login. So you can see a lot here off to the right, the start time, the end time. Some of this has been running for a while and it goes on and on. We can get more detail as we need it. So that's a good command. It's part of our lab. And then what we're going to do is we're going to go ahead and roll back that transaction. So let me do that. I'll find the transaction. I think we're talking about number 82 and 79. So here is what I'm going to do is I'm going to go to a separate line, and I'm going to just select the line here to only roll back. And we'll get that to happen here, roll back the transaction, so that's a good option. Now that it's rolled back, I can see it rolled back a couple of different ways here that I can go look at. I could run maybe this command again, and let's see if it executes this again. Yeah, now that it's rolled back, you notice it's been very helpful because I can get the other transaction to work. So there's a lot of ways to do it, a lot of ways to look at the information also. And what we're going to do is maybe adjust our isolation level and make it Read Committed Snapshot. This is a better approach. And what we're going to do is we're going to adjust it to Read Committed Snapshot on that database. What will happen is this will be able to do reads and writes at the same time. So this is an excellent option. So the reason we're having the issue here is because you can't read and write at the same time. But if we work with the option here, Read Committed Snapshot, it allows us to do that. So now we have 1,000 records here. Reading and writing, as we know, cannot happen at the same time, but we can make it happen with Read Committed Snapshot. That means if someone is doing a write, I can also do a read because it will take a snapshot of the data that I'm trying to read and put it into memory for me. And then I can read it from memory. So this does have a little bit of a downside because it will take up more memory, but we can do reads and writes at the same time. So we'll try this one more time, and we'll go in and we'll execute that there, and we'll begin that transaction. And so we want to make certain that the transactions are able to, that we can read and write at the same time here, and we'll put this in here for error handling, and we're going to commit it. And I'd like to say you want to do this usually between try and catch, which would be very helpful. So we'll begin that one, and then I'll come here and I'll run this one again. Let's see if this takes a long time to execute. Nope, it executed with 87 records back, and we were able to run them both at the same time. So this is good. It's not being blocked because we did that Read Committed Snapshot, and the sessions are very helpful also to, as we saw earlier, to kind of dig in and get more information out of it. You can also make these sessions through the wizard. So you don't have to use code. I can go into my session wizard here, and I can actually make a new session via these wizards, giving it a name. And then from here, I can say whether or not I want it to start the event at startup or not, and I can go back and adjust that if I'd like. And then there's a bunch of templates in here that I can use as a starting point that might make it very helpful. Maybe you want to do something to capture, query detail. Weight statistics is a good one. Maybe I want to capture that, so I can pick this from the list, and that will give me the starting point for that. And then I can go in and I can see what's going on, and I can go in and keep picking some information. So you can see what it actually picked there off to the right-hand side. Notice the start and the completed. And you need to capture whatever information you need to capture, you can add to that list. So I can go through the list here and see a lot more options that can be added. But the template gave us what's over on the right-hand side. But I can add to that. I can change the channel. I can work with different packages. I can also go in and work with our database. It takes me a moment to scroll down to it. It stores a lot of stuff in here that you can pick from. And then I can pick up maybe a good option in here. I can try to go in and pick up a few more things if I want, add those to the list. And maybe I want to pick up something like the deadlock report here under the database. That's a good option. And notice when I select it, it tells me a little bit more about it down at the bottom. And then it goes in and it can set up, it'll tell you the field that's going to pull up. And I can also click that little arrow there to the right to add it to my list. And that's a good one to pick up, where we can see the deadlocks, where you have resources vying for each other's where you have processes vying for each other's resources. And there we can see the session blocking. We can set that up. And this is where I can pick up more information just by clicking the box. And what do I want to pick up? I can scroll down the list, find the items, add them here. And then I may want to filter out the results because this could add in a bunch of information that maybe I don't need to pick up. I can use and or. I can use some of the different operators here and assign values to them. So a lot of flexibility there. And then I can also adjust some of the settings for the maximum file size and where I want to store it. And I can also, of course, in here, add into add the ring buffer as a destination and adjust its size. But once you've created this, you can go back in and make other changes to it if you'd like. But the wizard is a little bit more limiting. So I'm going to go in and summarize this. And then I can also copy the script out if I want. So I have a copy of what the script was to make this. This will take just a moment. And then it's going to add in and tell me that it looks like it's been created. And then notice it's right here, that test event session. And if I want to use it, I'm going to have to start it because it's currently stopped. So I can start it by right-clicking it there. And then if I expand it, I can see that it has the two destinations, one to a file, one to a buffer. And then I can right-click it, get into its properties, and make additional changes if I'd like. Thank you for viewing this section, and I look forward to seeing you in the next.